All right, welcome back to part two of this video. So here we are talking about the central limit theorem for means. That's the sampling distribution for means. Okay, last time we talked about what the theorem requirements were. Number one, simple random sample. Number two, samples of size n are independent. Number three, either the original distribution is normally distributed or n is bigger than 30. Under those requirements, the conclusion is that the shape of the sampling distribution is normally distributed, that the mean of the sampling distribution is equal to the mean of the original distribution, and that the standard error of the sampling distribution is the standard deviation of the original divided by the square root of n. Okay, cool. The other thing is, well, how do we do the probability calculations? Well, we're going to use normal CDF, and we just need to modify the mean and the standard deviation according to the formulas above. Okay, cool. Well, let's continue. So, couple notes. Number one, if the original distribution is normally distributed, then any size n we can use that for samples of any size. In other words, of course, small sample sizes. So that's really, really useful. This isn't true for proportions. This is only true for when we're doing it with means. So number two, if the original distribution is not normally distributed, then for samples of size greater than or equal to 31, okay, that's our assumption. Remember, n bigger than 30 or bigger than or equal to 31. Okay, that's the sample size we need so that we can assume that the um, sampling distribution is normally distributed. Number three, um, so I'm just saying, okay, as long as the samples are really large, that the sampling distributions will eventually be normally distributed, and that the sample means are an unbiased estimator of the population mean. So just, we've talked about that idea already, just wanted to emphasize it. Okay, now let's do some examples. So basically, let's look at part A. Okay, here it says use the assumption that neither the original distribution is normally distributed or that we have a large sample size. Um, Small typo, we need 31 here. Okay, so it says given a normal distribution, so right off the bat, we are starting off with a normal distribution. So this, let's call it this one OG for the original, the starting distribution. Sorry, let me make it in blue here. Okay, and it's telling us that the mean is 10. So let's draw a 10 right here. Standard deviation is 3. 1, 2, 3, 1, 2, 3. And we would add and subtract 3 to get the values of the tick marks. I'm not going to go through that since I don't think we need it for this problem, but just conceptually, that's the process that we're always doing. Now, this is the key that we need to be dealing with a sampling distribution. Because our sample size, that's the little n, is bigger than 1. Okay, n is 9, but it's not bigger than or equal to 31. However, because they told us that the original distribution is normal condition, so okay, let's go through the requirements. So we got to practice this. SRS check, independent check. So I always just abbreviate this stuff. And number 3, let me zoom in a tiny bit. Either we have the original is normal or n is bigger than 30. Since n is 9, this requirement is not true. However, we can put a check mark under normal because that was told to us in the statement of the problem. All right, so this is essentially how I'd like you to verify requirements. So it's pretty brief, but it's something that we got to do every time we're doing a sampling distribution problem. All right, well, what do we do with this? Given that the requirements are met, I am going to draw a little bit skinnier than the original, because remember, whenever we do sampling distributions, the standard deviations get a little bit smaller. So where is the center of this? We call that mu of x bar. And the problem asks, well, go ahead and find both of these. So mu of x bar. Well, the theorem is, if you go to our formula sheet, it tells us that mu, we're looking at this one right now, it tells us that it's equal to the population mean. So that is 10. So there we go. That's our first answer. What about sigma of x bar? Well, going to the formula sheet, it says, look at this formula now. Sigma divided by the square root of n. Okay, we do sigma divided by the square root of n. Now, the problem tells us sigma is 3. Of course, I'm looking at these two numbers here. And then I have to do the square root of 9. Okay, so let's go to the calculator real quick. I got my thing screwed up here. Sorry, bear with me just a minute while I try to troubleshoot. Darn it. Okay, I don't know what I did wrong. 1 second, please. All right, sorry about this. I'm gonna have to do this off screen. Maybe I'll pause the video and do the next one. Okay, well, let's see. I can do this one without the calculator. Square root of 9 happens to be 3. So we've got 3 divided by 3, which is 1. So highlighting the fact that, remember, if we started with the standard deviation of 3, and actually, let me go through these details here. This is pretty helpful. Let's put a 10 right here. Then standard deviation of the original is 3, so this would be 13, 16, 19. And then going backwards, it would be 7. Oh gosh, I'm so bad at subtraction. 7 minus 3, 4, and then 1. Okay, so look at those markings. So the original distribution has values between 1 and 19, roughly. Of course, we always got a little bit more outside of that range. Now, because the standard deviation is one of the sampling distribution, remember, we're going to call this the X bar distribution. Okay, and sometimes I'll call this one the X distribution because it's the original values. So when we think of these markings, the 1, 2, 3, 1, 2, 3, those are all based off of the standard deviation. Because the standard deviation is 1, this is also centered at 10. That's what the central limit theorem tells us, is that, okay, well, they're both centered at 10. However, the standard deviation is 1, so this is going to be 11, 12, 13, 9, 8, 7. Okay, so that's kind of a really nice illustration of what's going on here. The way to interpret this is basically when we take the average of all of the sample averages, it's kind of like a double averaging effect. Those are actually way closer to the original average than the original distribution. All right, let's do the next example, and then maybe I'll just pause the video here while I figure out my technical details here. Okay, so we've got the distribution given in this picture. Okay, so this is the X distribution. Of course, it's some sort of very bumpy, pretty random looking thing. But what it's telling us is that the mean of this, so I'm just going to pretend to eyeball the mean. Let's say it's over here, that is 77. Okay, so that's the info they're telling us. And the standard deviation is 14. So it's pretty big standard deviation, which we can see from this picture. There's a lot of variation in this data. 49, okay, that's our sample size. So the question is, well, what is the X bar distribution? So let's go through the requirements. Before we can find this, we have to check that the requirements of the central limit theorem are met. Simple random sample, check. Independence, check. We always just assume those. Number 3, either the original X is normal or the sample size is bigger than 30. Now, we this time are not told this information. And in fact, look at the picture. They give us the distribution. It's definitely not normal. So look at our sample size. Our n is 49. That means this is satisfied. That means we can put a check mark. So 1, 2, and 3 are satisfied. That means that the central limit theorem tells us that the mean of x bar is equal to the population mean. Sigma of x bar is equal to the population standard deviation divided by the square root of n. Okay, where am I getting those formulas? I am looking at my formula sheet, and I am getting them from that. Okay, well, I will do these calculations off screen here, since I'm so sorry I can't sync up the digital calculator. But let's see, for the mean, I don't need to do any calculations. It's just 77. Okay, it tells me that right here. For the standard deviation of the sampling distribution, it tells me it's 14 divided by the square root of 49. Now, square root of 49 is 7. So these numbers are cooked up a little bit. So 14 divided by 7 is 2. Unless I am very bad with my arithmetic this morning. Nope, I'm correct. Okay. So what do we do with these numbers? Well, remember, there's another thing that the central limit theorem is telling us. It's telling us that the shape of the distribution is going to be normal. So x bar distribution is in red, is normally distributed, and I always make it way thinner than the original. Remember, the original standard deviation is 14, but the standard deviation of the sampling distribution is 2. The centers of both of these are 77. Okay, so they're both basically centered at the same thing, but the real magic is that the tick marks, as I like to call them, are now just based off of the number 2. Okay, so I'm not going to draw them for the x distribution in blue, but I can draw them for the x bar distribution. 79, 81, 83. Again, because I'm adding 2, and then I can subtract 2. Subtract 2, you can see how slow my brain is at subtraction. Okay. So those values are really clumped together, whereas the original values, if I was to, put them where the standard deviations are, they're going to be based off of that number 16. Okay, so good. That is great example just to kind of set up what we're going to do. Let me pause the video. So I guess I'm going to have to make this one a, oh, wait, no. Let's cover this page because I don't really need the calculator for this. And then I'll do part 3 when I finish this. Okay, why is the central limit theorem so powerful? Let's go through this. Again, this is kind of the big result in statistics. But it's super theoretical, which is why I decided to kind of make it a video here so you can kind of watch it, pause, think, and return to it as many times as you need. Okay, so in many situations, knowing the shape of the original distribution is impossible. By the central limit theorem, as long as we are willing to compute probabilities of samples of size 30 or more, instead of an individual sample, we can use the normal distribution to compute probabilities. Okay, and remember, the big idea of the last chapter was that we can compute probabilities of normal distributions using normal CDF. Okay, now I really like this example. This is great exercise or example for intuition. Let's kind of think through these and I'll pause so that you can kind of think about them before we answer them. So as the sample of size n increases, the distribution of sample means becomes, okay, well, as we have bigger sample sizes, what's happening to those sample means? Well, shouldn't they get more accurate to the original? So what's happening is that the variation between the samples gets tinier and tinier. So the answer here is A. The reason is, again, as samples get bigger, our sample means are actually measuring the true population mean more accurately. Okay, part B. According to the central limit theorem, the mean of the sample means is, well, the mean of the sample means, it's a weird tongue twister, but we've got good notation for that. Well, the mean of the sample means is the population mean. So, which one makes the best sense here? Less than the population mean, the same as the population mean, or more than the population mean? It's the same. And of course, I try to keep the multiple choice brief, but this is assuming that the 3 requirements are met, which we'll of course assume that. How about C? According to the central limit theorem, the standard deviation of the sample means, we've got notation for that, is, okay, central limit theorem tells us it's the standard deviation divided by the square root of n. So let's kind of think about what this formula is telling us here. Well, I'm dividing the original distribution by a number. Okay, and imagine a simple number. Let's say imagine our sample size is 100. Well, what's the square root of 100? I'll just tell you, the square root of 100 is 10. So as an example, if we have a standard deviation and we divide that by the square root of 100, it's basically saying, take the standard deviation and divide it by 10. That's making it smaller. Okay, so for the standard deviations, they're actually less than the population standard deviation. Okay, so these are excellent questions for, just reviewing the key ideas. All right, we've got one more. In practice, if the sample size n is at least 30, we can assume that the distribution of sample means is normal. Okay, so that kind of summarizes the big ideas of the central limit theorem. So just to wrap up, when do we use the central limit theorem? The key here is when we're dealing with samples bigger than 1. Okay, and of course, this is just reminding you, we got to check our requirements. Check if the distribution is normal or greater than 30. Then we're going to find these using the formulas in the formula sheet. I always recommend, and not recommend, I require that you draw a picture. This is how you prove to me you understand what all of the symbols and formulas mean. And then once you've done that, of course, you just use normal CDF to compute the probability. Okay, wonderful. So this is the big GTQ for this section. So notice we're practically done. We just have this last page to go. So why don't I pause the video here, and when we return, I'll have my digital calculator set up. See you next time.